This talk will be by Dan Szabo. He's the lead programmer at DragonBear Studios, and he'll have a talk on state machines and editor tools. So welcome to the stage, Dan.
Hey, good to be here.
Here you are. So first of all, do you want to, I guess, quickly introduce yourself and sort of say what your talk is about and who it's aimed for, I suppose?
Yeah, absolutely. So I'm Dan Szabo. I'm the lead programmer at DragonBear Studios. We're working on Innchanted, which is a co-op management game, which has some AI in it. I'm going to be talking a little bit about the AI that we've used over the last few years in that game and a couple of other games I've worked on as well. Just going through the kind of struggles we've been through and also like a few solutions that we found that were really helpful there too. It's typically aimed at simpler AI for indie games. So indie games be mostly focused, but a lot of what we're talking about is kind of transferable because we're talking a bit more about the processes, practices behind how to get the most out of debugging.
Sweet, awesome. Well, that sounds like a great talk. Without further ado, I'll let you get on with it.
Awesome. Cool. I might just head into the next slide because we've kind of gone over a bit of this already. So yeah, specifically in the context of Enchanted, I'm going to cover like the evolution of our debugger. So if there's one thing you can walk out here, it's just how important it is to think about meaningful debugging, and we'll be going into a bit of like the logs and system design, all that kind of stuff. So let's start with a quick run through of the AI of Enchanted, which is nearing the end of its development. So here we've got an AI running around the inn. It's attached to a customer. The player said, "Go serve some customers." So it's just attached itself to the one on the left there, and it's crafting a red steak. And then halfway through, the player said, "Oh, go defend the inn. There's a thief coming in, trying to steal money from our piggy bank." So it's successfully gone and thwarted them off. And then the player said, "Go resume serving," and they've found the best way to get to the customers to throw something over the river as the shortest path. So it does a little victory dance, and so far the AI is going really well. Pretty proud of it. But the key part here was it needed to do most things a player can, and it needed to pick up things on the fly, read world state, all this kind of stuff. So it started simple, and then it expanded to cover more and more behaviors as development progressed. So here's a couple of examples. So the first one is we're navigating through portals. So pathfinding became a bit more tricky. And then this is where it's got a waiting point where it tells the player, "Hey, can you go hit this lever to make that cauldron over the left-hand side come towards me?" And then, like all games, we needed fishing. So this is actually more of the one of the more specifically complicated ones where not only was it just getting an item, but it needed to know that I need to find a fishing spot. I need to get a spear first, and I need to go fish for that and then cook it before I can serve it to a customer. So a lot of this wasn't directly accounted for as the game experience. It's pivots and evolution that's really common for development. So what ended up happening is we wanted the AI to be relatively predictable and less emergent. And in a way, this defeats the purpose of the paradigm of the system we were using. So I'll get into a bit more about what that was. So it was called goal-oriented action planning, which I'll refer to as GOAP from here on, as opposed to like a standard finite state machine. There's a bit more to it and some complexities that come with it. So I'll cover a little bit about that as we go through. And it's not so much that GOAP was the wrong system to use, but it did add complications that we could have avoided if we used, say, a standard state machine. Cool. So when we started developing all this, it was all done with resilience and modularity in mind. But in reality, there's going to be bugs, and players are going to do really weird things to confuse the AI in new ways. So for example, in Enchanted, you can combine items on a table to make fancy recipes, but with humans, if there's no free table, the player's just going to adapt and free one up. So let's see what happens when the AI is put in the scenario. So over here, these are our free tables here. well, they're not free tables, there are crafting tables, and they're all full up with stakes. And the AI is trying to figure out how to craft a blue stake, but it's got nowhere to put it, so it's getting caught in this loop, and now it's throwing errors, and it's all a mess. So we need to figure out where this is failing. But before we jump into our debugging attempts, I'm just going to briefly touch on the high-level components of the GOAP system to know what we're up against, and just give a bit of context around that. So GOAP, meaning goal-oriented action planning, implies we're attempting to achieve a goal through the use of actions. So goals are those high-level targets, such as serving a customer, defending an inn. Actions are those smaller tasks that achieve that goal, like retrieving items, cooking, crafting, delivering. And then we have senses to observe the outside world, such as customers, what orders are available, what's achievable, and the memory, which is the agent's internal state, or the AI's internal state, containing, for example, what customer are they assigned to, what are they holding, all that kind of stuff. The last two key components are the planner and the executor, and we'll focus mostly on this. And the planner validates goals and actions and uses an A-star algorithm to find the most efficient action plan and passes this to the executor, which executes it. So the strength here in GOAP is its ability to plan a set of actions during runtime based on the world around it and find the most efficient path to achieve those actions. So essentially, you don't need to create transitions between actions. It's all calculated on the fly. But with it comes a bit of complexity. So when something goes wrong, it's either going to be in the planning stage or the execution stage. So we'll start with the planner. And there's going to be an issue with one of the actions, but we don't know which one, and we don't know where the error is within that action. So if we log out everything the planner's thinking, it's going to be noisy, like really noisy. So this here, we've got this is about 5 seconds of runtime, where we already have over 1,000 logs. And there's no way I'm going to give anyone the task of sifting through this to trace through where the error started. So we need something smarter, lest we run into sort of this situation. I do love this guy, but this is scary. So we can, of course, combine this with breakpoints to get even further, but it's still pretty cumbersome. So yeah, let's go on this debugging journey. So yeah, like any good engineer, I weighed up the different methods of debugging, and here's one solution. Just have an intimate knowledge of the AI system. We can solve anything. We're engineers. So spoiler, we didn't entertain this for very long. It wasn't working out. So let's be a bit more realistic and find the clarity amongst this chaos. So we started by throwing the AI state and the execution status into the inspector. It helped solve a lot of bugs and point us in the right direction before we managed the code. And while it was better than the verbosity of the planner and the execution logs, it wasn't quite there. With a good knowledge of the AI system, it wasn't too tricky, but consider when you haven't touched the AI for a year or even months, and or having a new developer enter the debugging game. It's a tough ask. So take, for example, this section of the planner code, and I'll step through a bit about what this is doing. It's not too important that you follow this exactly, but this is called whenever we want to formulate an action, and it's called really regularly. And the key part we're interested in here is the third, or is the if statement in the middle, which validates the actions by A star. So that's where most of the effort's spent. So yeah, here, going inside this and placing some breakpoints is going to be a bit tricky. If you're familiar with A star, then you might be familiar with how it's going to traverse these nodes time and time again. And some of them are going to be correctly invalidated because they're checked multiple times, and sometimes they're not. So we need, what we really needed was like a summary that grouped logical chunks of the planner rather than giving instantaneous updates over time, which is what we saw in that console output before, which is just horrendous. So yeah, I want to focus on what it means to have meaningful logs for a minute. The most critical piece of information we want to know is when a check fails. So when we write a check, at the time we write it, we know exactly why it fails because we wrote the logic. So let's record this and pass it to the logger. So here's an excerpt of one of our actions, and I'm going to step through this. So this is from the craft item action. And the best part about this kind of method I guess we're using is it encourages documentation and reasoning for the logic as we go along. So in this snippet, what we want to do is validate a crafting station based on the AI state. So first we check if there's any remaining items, and if there aren't, we realistically have nothing to craft, so we should exit the action with a failure message, no remaining items for crafting. And next, if the AI is about to retrieve an item that the crafting station doesn't need, then we know the crafting station state has changed unexpectedly. So again, the action should fail, and we give that message. And then finally, we're as part of our system, we require any cooked items to be handled by another action first. So that means if any remaining items need to be cooked and the AI isn't already holding that item and about to add it, the action should fail again. This usually occurs when a player takes a cooked item from the crafting station. So we should provide a meaningful message that tells us just that, which it does. So for scale, at the time of writing this presentation, Innchanted had 32 actions with a total of 83 action failure calls. So it's kind of granular in a way, but it's also really easy to maintain. It's not a huge number. And we do put emphasis on ensuring this is right when we're creating new AI behavior, because it's really worth it when it comes to debugging. So all we needed to do now is pull this into a custom editor window. It's really simple, but it managed to solve about 95% of our AI issues without having to search through the code for where the debugging was, for where the bug was occurring, because it told us directly. So over on the left, we have our AI memory, or the AI state. So the AI state is a dictionary with an enum key and an object value. So all our states kept together, making it really easy to read in our editors. So like Booleans at the top, where red is false, green is true. And then our objects are down the bottom here. At the top right is our execution status. So it's telling us what the current goal is and the action plan to achieve it. And then arguably the most important part is the log down the bottom right. These logs are also logged in a separate file during runtime. So that's really helpful for when, say, we pass a build off to QA, and then they give us a video back, and they can give us those logs as well. And they might not have access to this because they're not running it in the editor. So there's a couple specific lines of interest here, and they're pointing us towards an error, which is the error that we saw when they're constantly recalculating. If you recall that video just before, where we had no free crafting stations. So let's take a look at what the repeated error is telling us. It says craft item action, procedural precondition check failed. So this points directly to a function within the craft item action. It's telling us exactly where the error is. What it does is it rules out event-based failures or like action failures, and rules out recalculation inconsistencies and things like that. So we can check this action directly, and what's in here isn't too important. It's just the fact that this is the function that is invalidating the AI behavior, but something else isn't, which was in the planning stage. So we're running our execution stage, and the planner isn't invalidating it properly. So there has to be some discrepancy here. Cool. So going into what's in the in the execution stage, we have the check procedural conditions function is what we were told was the error. So the begin is fine, the onTick is fine. This is pretty much everything that makes up the execution stage of the action. Then on the planning side, we have two parts to it. There's the effects and preconditions check and a components check. So the effects and preconditions are working because the A star, well, that's part of the A star section of the planner. And we know this is working because the executor status shows us like that those actions are being called as we expect. So we can rule that one out. And we know the error has to be in the check components method, or the inconsistency rather is in the check components method. And it turns out it's just checking for a different set of rules. So all we need to do was align these and our bug was fixed. This typically happens when you make a small change here, a small change there, and you don't sort of have a overarching method that it can call to check things properly. So yeah. So the takeaway here is all we need to solve most of our AI issues was just a well-placed log. Again, I love this guy. He's so good. So yeah, it's worth comparing the GOAP solution to a traditional state machine. And the key point we're going to focus on here is visualization. So This is taken from a side project I'm working on, and it has a simple AI set up for enemies. So it's a 2D platformer. You can run around and dodge enemies or attack them. Yeah, we wanted the AI to be customizable as well. So you're reusing the same actions and just changing a bit of the properties to get slightly new behaviors. But I knew I wanted to use a finite state machine here because I knew the AI was going to be simple and predictable, and there's not going to be an excessive amount of transitions between states. Okay, so this was the custom editor that was built for it, and it was built with debugging in mind from the start. So it has a visual node editor, which is used really similar to the, I guess, the animator in Unity, if you're familiar with that. And then we've created a filterable log system. So I'll get into that in a later slide. And we can modify those action properties during runtime as well without affecting actual data. So it's just, yeah, really useful to sort of play around with something visual. It's really fun to use too. So here we've created an AI module for an enemy that's a clone of the player. And its goal is to patrol until the player is in range and then pursue and attack them when it can actually hit them. By the way, this project's open source, and I've linked this in the presentation if you want to go check it out later. And this is what it looks like. So I'm going to play it first and then talk about it again and play it. So the red AI there is chasing our player. We're the blue one. And it's just relentlessly going and trying to kill us. And it managed to kill the player without any problems. So let's play this again and talk a bit about what's happening. So during runtime, we can select any running AI to see exactly which action it's running, which is highlighted in yellow. So here it's got the patrol state highlighted. And if we play that again, we can see once we get in range, it's gone to the follow threat action. And when they got in range again, they went to the light attack action. Cool. So we can see exactly what's happening. And then if we click the logs tab in that editor, it shows us the AI's action transitions and state changes. Not important that you can read this, but there's these purple lines, which are the state transitions, and then everything else is the, I should say the action transitions as opposed to the state changes. The state changes are the lighter blue color, and we can filter those out if we're, for example, if we're not interested in the is jumping state change here, we can just right click that and click suppress logs for that particular state. And if we want to bring it back in, we can just click on the left there and re-add it. So pretty simple to use. And we also have the state at the bottom left there, similar to what we saw in the Innchanted project. So combining this, the visual runtime of the state machine with a detailed state, we can debug things early in development and catch our pain points really early on. So for example, in this, it's a still image, but it may as well be a video. The red AI there is stuck against a wall and it's not knowing how to turn around. And if we look at the AI's state, it's stuck in the patrol action. And well, actually, let's check the editor window. So it's in the patrol state, and in the image we saw it was stuck against a wall, but the is near right wall state is set to false, and it should be true, so it knows to turn around. So this points straight to a bug within the state transition itself. So I'm just going to compare the two systems we just looked at. So the GOAP versus FSM solutions. And yeah, it's worth spending time being realistic about the system you want to use for your AI. So in the GOAP we use for Enchanted, it's easily scalable because we can just add actions and we don't have to worry too much about transitions. And action efficiency is handled at runtime if it's set up properly. So you can set costs per action. However, it's hard to visualize well, and debugging requires an intimate implementation knowledge as well. On the other hand, finite state machines, they're really intuitive setup and they're easy to visualize, but they are less scalable if you have a lot of actions and a lot of transitions. If you've worked with the Unity animator system and you've got tons of animations, you might be familiar with the web that can become. It's a similar thing here. And states and transitions, they're hard-coded as well. So yeah. So GOAP, for example, is excellent if you want to add costs to certain actions, for example, assigning a weight to movement and then picking up an item. And it's great for pseudo-emergent behavior where you have multiple ways to achieve a goal, like a city builder where your workers need to either buy or craft tools or go to go build things, or if you can collect resources in different ways. Whereas state machines, on the other hand, are great for predictable behaviors, like in a 2D platformer with simple enemies, or to be honest, even management games like Enchanted. But yeah, that's pretty much it. So I've got a few resources here that inspired a little bit about this talk. I'll go into a bit more detail. So the first link there is does talk a bit about documentation. The second one is just saying AI can be simple, and it's a great consideration to have. Simple AI is really effective. The AI in Games YouTube channel is really amazing. If you're interested in just more weird and wonderful things that people do in AI, go check that out. There's some links to the GOAT project if you're interested in how GOAT works. And down the bottom there, I've got a couple links to the 2D platformer project. So I've got the AI link there, and also the editor tools, which are completely reusable as well. But that's everything. Cool. Thanks so much for listening.
Brilliant. That was a wonderful talk. Awesome. Thank you so much for sharing all that information. It was super cool finding out how all that works. We have a few questions. We have 2 questions about everything that's been going on. So Guri asks, if we're using A-star to find the goal state for AI, what methodology do you recommend to choosing the correct heuristics?
Yeah, really interesting. So what it does is it assume in Enchanted, it was really simple. We just assumed every action was just a single float value, like just a 1. And everything that costs more, we just gave it a higher value. So for example, if you need to walk halfway across the map, we would sort of calculate that and just go, okay, we can assign a higher weight to this. And yeah, essentially the best way I found was just to assume your actions are going to be 1. There might be a much better way to do this, but yeah, you're just trying to find something the least amount of actions possible. So yeah.
Yeah, awesome. Yeah, right. That makes sense. Yeah.
Yeah, I think that's a topic we can talk about like in depth. But it depends on the system, I think, as well.
I feel like there's a lot of things that could be explored here. I know a few people in the comments are like, I just want to find out tons more about this. So yeah, we had one other question from Quinton who asked, you sort of talked about this a little bit, but why did you create a custom editor and log? And like, what does the default log lacks that's important about what you've added in?
Yeah, the main thing about taking it out into a custom editor window was separating it from everything else. We have a lot of systems in the project, and we wanted to just focus on the one important thing. It also gave us a way to filter out, for example, if we wanted to split out our planner logs to our execution logs, we could even split that out in the editor just by giving it a type that we can filter on. So the logs themselves don't just necessarily have to be, here's a string, go log it. It can hold some state about where it came from. You could even have the execution state that it's in there as well.
Yeah, awesome. Okay, yeah, sweet. That's cool. All right, I think that's all the questions we had. So yeah, thanks so much for your talk, Dan. I really appreciate it. It was wonderful. Feel free to tell us where people can find you. Like if they want to ask you more questions, are you going to be hanging around the Discord or anywhere online?
Yeah, I'm happy to hang around the Discord. I don't know how to, but definitely ping me. You can get me on Twitter while that exists, and LinkedIn. I've got a reference there as well, or through DragonBearStudios.com or Enchanted.com. Yeah, so I guess I'll just hang around the Discord.
Yeah, brilliant. Awesome.